So we have this afternoon's long session kicking off now. So Gurtej will talk to us about sampling for Lattice QFT, right?
Yeah.
Lattice QCD in some sense.
Yeah, it'll be in there, yeah.
I think this will be new for quite a lot of us here, so I'm hoping there'll be a lot of chatting and asking questions, at least to get started, because 3 hours of not understanding probably isn't fun for anyone. Right? So really get involved. I certainly hope.
Yeah, feel free to interrupt at any time.
Yeah. As I said, we have 3 hours. We'll probably take a couple of breaks along the way when it sort of naturally punctuates things. But yeah, I think we can get started. So I'm looking forward to this.
All right, thanks, Sam. Yeah, so also thanks to Michael for the very nice overview. So some of the topics that are relevant to statistical lattice simulations are also very much relevant to lattice quantum field theory. And at the end of the day, actually, the idea will be to formulate the physics question that people try to ask in this context in the language of statistical physics. So we'll end up with something that looks quite similar to the Ising model, in fact, where you have some kind of energy model with a probability distribution described with positive definite weights that one tries to sample. But before we dive into all that technical detail, I did want to just give sort of start off with a bit of a high-level physics motivations. So I know people here are not necessarily so interested in the physics application of this, but I want to paint a picture of why this problem does have some impact and is important to try and improve our techniques upon. And then go into the fundamental basics of how the problem is formulated and how that really ultimately reduces down to a statistical sampling problem. And so then sort of the second large chunk of this talk will be in actually addressing how people in practice do this sampling via Markov chain Monte Carlo. Our methods are not necessarily particularly advanced, and I think there's a lot of room still to this day in ways that this sampling approach could be improved for even the largest scale calculations. So I would certainly love to have a bit of a dialogue or a conversation on whether there are new ideas that, that perhaps from the stats side could be pulled over into these QFT sampling problems. OK, so I'll just start with a bit of a presentation in the slides of this high-level overview and motivation, and then the idea was to move over to the Blackboard. So apologies for this kind of dual lecture here, but that way maybe we can write down a bit more of the technical details at an appropriate pace mathematically on the Blackboard. OK, so really the motivations, I would say, for quantum field theory, this very imposing sounding word, but I promise it's not as scary as it sounds. So I would argue the motivations come from the standard model of particle physics. And so you can see here on the slides, might be a little bit difficult to read the labels, but this is a cartoon picture of all the ingredients of the standard model, all the fundamental particles we believe describes the physics of the world around us to a very good degree, excepting gravity, but that will not play any role in this talk, unfortunately. We don't yet understand how to tie that with this model. But so the standard model is a theory of these fundamental particles and their interactions and the way they bind together at the smallest of scales to form matter at all scales that we seem to be able to perceive. And it divides up into several different sectors. So maybe I can actually point this out in the slides here. So on the top left, we have the quarks. So this may sound familiar if you remember back to what composes nuclear matter. It's really mostly the up and the down quarks, which bind together in certain ways to form the proton and neutron. And those bind together to form nuclei of atoms and then molecules and so on. So this is, of course, very important to our everyday world. There's also heavier cousins of the up and down quarks, which won't really play a role for today. There's the charm and strange and the top and the bottom quarks. This you may have heard in passing. But essentially, they share many of the same properties as the up and down quarks and just happen to be heavier. And likewise, we have this kind of ordinary looking list of particles in the left side of this bottom left corner, which is the so-called leptons. And maybe the most familiar one here is in the top left of this bottom left corner, the electron. So of course, together with the protons and neutrons formed out of the up and down quarks, the electrons really play a huge role in chemistry and forming the molecules and the bonds of the matter that we interact with on a day-to-day basis. But the electron has some heavier cousins. There's the muon and the tau. And there are also these light, weird other cousins of the electron, muon, tau, known as the neutrinos. Maybe these words are familiar, but for today, actually, we won't focus really at all on the leptons. This story will be mostly about the quarks and the strong nuclear force that binds them together within the standard model. So I've only now talked about the left side of this diagram. There's also the right side. And these are particles that may be less familiar, excepting maybe the photon, which is drawn here in the gamma. So the photon is the force carrier of electromagnetism. I imagine this is quite familiar, but there's also these less familiar particles, the two W's and the Z, which carry the weak nuclear force. And then there's this weird colored gluon over here, which carries the strong force. And so in fact, the gluon, the carrier of the strong nuclear force, is a key component also of the story of today, because it interacts with these quarks, in particular the quote-unquote color degrees of freedom. It has nothing to do with optical colors, just a fanciful name. But it is what binds together quarks into protons and neutrons. And ultimately, protons and neutrons get bound together also by this gluon, and I guess the emergent forces and particles associated with it into nuclei and therefore the cores of all the atoms and molecules that we see around us. So perhaps also relevant, you may recall in, so I guess I should mention that the standard model is itself a quantum field theory. And I'll say in detail what I mean by a quantum field theory, try and decompose these words a little bit in a moment. But it is a very minimal description of particle physics in the sense that very few free parameters and a very parsimonious set of equations describes all of the interactions of these maybe strange-looking particles in the bottom right. But I did want to mention that, yeah.
Can you mention exactly what the free parameters are?
Sure. Yeah, so actually, maybe now is a good point to mention that. So this is going to be a good test of my memory as well. So we've got free parameters that have to do essentially with the masses of almost all the massive particles in this list. They're not really fixed by the theory itself. And then there's a few free parameters associated with the interaction strengths of these three fundamental forces, the electromagnetism, the weak force, and the strong force. And in addition to that, there's a few relevant parameters having to do with how these families relate to one another. So how, for example, the up and the down type quarks in the bottom and top row of that picture, as well as the up and down leptons, so the electrons and the neutrinos, happen to relate to each other. So
basically, maybe the framework is, I want to know how powerful these forces are, and I adjust everything else to get something that makes sense.
Yeah, if you like, all of these parameters are fixed by deriving observations from the theory and tuning the parameters to match a given small set of observations, or maybe not such a small set.
The observations are, no.
Sorry?
So the observations are on how strong the forces, or
among other things, yeah. So actually, this is maybe a good point to jump to exactly the next piece of the slide, which is, so the things that we observe are things like how strong the force is, which can be quantified in some sense by this sort of a plot where I'm describing how frequently I see particles scattering off of each other as I increase their relative energy. So that sort of tells you how strongly they want to bounce off of each other. And you see some weird features like a rapid increase in some energy range of the number of scattering events and then a decrease again. And this is indicative of some kind of intermediate particle being created and tuning exactly towards the energy of that particle. So in this case, the Z force carrier of the weak force. And so you can see on here is a black line showing the theoretical prediction compared against many, many data points which happen to agree very well with this. So that's the sort of thing that would constrain the parameters going into this model. And indeed, once you constrain those relatively few free parameters, you do reproduce a lot of these observations. So also down here, you have a set of observations of simply particles that can be created in these sorts of colliders at various energies. And those particles can also be predicted, the masses of those particles, for example, and their interaction properties. And that seems to line up very well with the measurements, even though there's many more observations than the number of free parameters, suggesting that there's some correctness, of course, to this model.
Is it a bit like fixing our thermodynamic parameters and our interaction constants?
Yeah, I would say so. So you take some kind of maybe macroscopic observations after putting in some set of parameters, and then you tune the parameters until those macroscopic observations align. Yeah, exactly. Okay, great. So this is a bit of an introduction to maybe why quantum field theories are relevant, because this very important model in particle physics is described by, well, such a unified quantum field theory. But also, I should mention, the ultimate goal in this sort of an area, I would say, is to try and understand not only how does our physics come from this very nice model, but also in what ways does the model need to be extended to answer the questions that still remain. And there are several big ones. So, of course, you must have heard of dark matter, this unobserved but clearly present matter out in the cosmos, as evidenced by a number of things, but including its sort of gravitational signature. And so the question is that also a particle? Do we need to add that to the standard model? And if so, how does it interact with the particles that we know and love? Is there some kind of overarching, maybe fourth or fifth force that connects these particles to each other in some very weak way, which is why we don't see it on Earth? We don't know the answers to those questions, but the idea is to build a framework of being able to calculate things in quantum field theories so you can take candidate models and try to match them to predictions. Okay, so I've also mentioned that there's these very light cousins of the electrons, the neutrinos. In fact, the standard model claims that they're massless. They're not. We have observed that they have mass. They're just very tiny. So the question is how exactly to add the mass to the standard model. That's one of the open questions. There's a number of ongoing experiments to try to answer that right now. And maybe at a more kind of fundamental level, we actually know that there's a very significant asymmetry between the amount of matter and antimatter in at least our local universe. We're almost exclusively made of matter. And that's a bit at odds with the fundamental symmetry between matter and antimatter in the standard model. So there's a question of whether the standard model as a quantum field theory needs to be modified in some ways to account for this observation that we see in the cosmos. And maybe having a better calculational handle on quantum field theories in general will give us an idea of how such a modification could be made. Yeah. Sure. So this I didn't mention in this slide, and I should have, thank you. So each of these particles have an antiparticle partner. So the antimatter that we might expect to see is something like an anti-up quark or an anti-down quark, or an antiproton composed of these anti-up and down quarks and things like this. And in principle, that should occur with roughly equal abundance to the protons and neutrons and up and down quarks that we do see, but we don't see any of that really in our local universe.
And do the same forces apply respectively to the anti?
They do,
In the
yes.
same way.
And this is at the heart of why we expect some kind of symmetry between the amount of matter and antimatter we see. Yeah. There's some more details here, but I don't want to drown you in the physics of this talk. So maybe this is just a bit of a sketch as to why there are open questions that we are seeking to resolve.
Right, that broken symmetry similar to this broken symmetry we see at phase.
It is one possible explanation that, yeah, somehow it's spontaneously broken, or, like we happen to be in a region where things are mostly, let's say, matter aligned instead of antimatter aligned. But there's not really a good precise model that describes things in that way. And so concocting such a model and then making predictions from it is an important step somehow. Okay, so to actually answer these questions, as I've been kind of alluding to, requires taking theoretical predictions from the standard model and confronting them with experimental observations. So this is exactly going back to the question of how do we fix these free parameters, but also how do we kind of fix our understanding of the theory. And on the theory side, there's a number of approaches. You may be familiar with these kind of sort of famous looking Feynman diagrams where people draw these kind of squiggly lines and interactions between them. That is one approach that one can take. And another approach is more computational. And in fact, there's a reason to use both. So we now sort of get to the connection to the lattice part of the title, which will eventually connect to the statistical physics here. But I would break down the sort of theoretical approaches into two categories, one of which is these perturbative methods, which take on the form of these kind of drawing out Feynman diagrams, doing analytic integrals, and so on. And that works quite well for the electromagnetic and weak forces, so two of our three fundamental forces, but unfortunately breaks down when we want to treat this strong nuclear force, which is described by the so-called quantum chromodynamics sector. So again, remember that there were these three colors, so that's the name chromodynamics. Again, has nothing to do with optical colors, but it's just a sort of fanciful way of describing the degrees of freedom in the theory. So that part of the theory, which talks about the strong nuclear force, cannot be treated with this diagrammatic perturbative method where you do some kind of expansion. And instead, one must resort to quote-unquote non-perturbative methods, and in particular, the most successful of these is studying a quantum field theory on a lattice discretization. And so let me say a little bit about what I mean by that. So generally speaking, we have some kind of space and some time coordinates on which one has to define these fields. And I'll say more precisely mathematically what that means in a moment. But the lattice here is a discretization of that space and time coordinates into some discrete lattice of coordinates that one can access. So restricting yourself not to an arbitrary choice of x coordinate, an arbitrary choice of time coordinate, but a few discrete, maybe many discrete choices of time and x coordinates that one can sample. Excuse me, I should really use that word carefully. Restricting yourself to a specific lattice of space and time coordinates that one can access, upon which we define these fields taking values at points of this lattice, as well as on the length of the lattice, which we'll get to in just a moment. So this kind of a formulation where we've discretized what we think is actually a continuous space-time just acts as a computational trick that lets you then do these sorts of calculations where you go from the theory of here, the quarks and the gluon interactions between them, into a theory where we put the gluons and the quarks somehow onto the lattice, and then we do some kind of statistical approach to measure average properties of these fields in the lattice, which has to do ultimately with the physical properties that emerge from this physical theory. Okay, so that's a very high-level overview. Of course, we don't have time to go into all the details of what one might calculate, but I did want to point out one compelling, maybe motivating example, which is an ongoing tension which has received a little bit of publicity recently. So Michael actually mentioned these little magnetic moments that occur in magnetic materials, right? And they might align, and then you have some larger magnetic domain. So all fundamental particles, almost all, have some associated magnetic moment, and it's really the alignment of these that build out the local little magnetic domains and then further alignment in the Ising model even. But in fact, those magnetic moments are something that you can compute or predict from the standard model. And so a very interesting ongoing calculation has been happening in terms of trying to predict the magnetic moment, so the strength as a bar magnet of the muon, which is, if you'll recall a few slides ago, just one of these heavier cousins of the electron. So why the muon? It happens to be very sensitive to possible new physics effects. And so one can predict it very precisely from the standard model, one can measure it very precisely and compare these two numbers and ask whether there's any sort of discrepancy there, suggesting that the standard model really needs to be extended. And if you look at the state as of 2020 of these measurements, so on the x-axis is some kind of rescaled and subtracted version of these measurements. We have in this green bar the standard model prediction, and in this purple bar the experimental measurement. So there was some kind of tension as of 2020. And just like to highlight that the error on the standard model prediction is largely dominated by these bluish looking components. There's actually two other components in here, but they're this tiny sliver which you can barely see at the top of the pie chart. And the rest comes from this quantum chromodynamics, QCD, or in other words, the strong nuclear force effects within the standard model. So that's the big challenge to getting the error bars down. And precisely, literally just measuring, well, the magnetic strength of the muon, which has to do with its spin, exactly. Yeah, so you're literally taking muons, you're trapping them somehow, and measuring how strong they are as bar magnets. And that can be done very precisely, and it can be predicted very precisely. Except, well, there's an ongoing mystery because certain more recent calculations of these very challenging components have given a different error bar of the standard model prediction way out to the right, and different inputs also to pin down those parameters, as we were talking about before, also give different predictions. And we also recently, as of this past summer, got some new experimental data that reduced the error. And so there's still a slight tension, but mostly there's a puzzle on the theoretical side of, did we get it right the first time or did we get it right the second time? And if we got it right the first time, it's looking like we've discovered new physics, but unfortunately, we can't be sure until these ambiguities are resolved. So keep maybe this in the back of your mind. This is one of the many motivators for just trying to get a more precise handle on this QCD sector of the standard model.
When you say that it's very easy to predict, you mean analytically or by computation, like numerical?
It's a massive endeavor involving both analytical for certain pieces of this prediction and numerical calculations via Lattice QCD, in fact.
Okay.
Yeah, so exactly. Lattice QCD plays a big role in this prediction in the end. Okay, so let's talk about a little bit more about what I mean by putting a quantum field theory on a lattice. This is a lot of buzzwords, so let's try to be a bit more precise about that. Okay, so I mentioned already that there's this perturbative approach that one can take. We can forget about that for now. That's a different approach to physics, and rather we'd like to focus on this non-perturbative approach based on defining a space-time lattice with some kind of lattice spacing, which I'll just call A, between nearest neighbor sites, and some degrees of freedom that are assigned to the points and the edges of this lattice. And so being a space-time lattice, just keep in mind, this is 4-dimensional, but I can't really draw that, so I'll just draw 3D slices typically of this lattice. But there is an extra 4th dimension attached to this. And ultimately, the idea would be that if you can run some simulation for a variety of different choices of lattice spacings, and then extrapolate as A goes towards 0, you'd recover a prediction about the true continuous dynamics of these degrees of freedom. So this is going back to Michael's point that kind of in this context, what we care about is to do sampling. Ultimately, this will turn into a sampling problem. So we'd like to do the sampling at a variety of different choices of these hyperparameters, which ultimately determine the lattice spacing, and then take some kind of extrapolation or do some analysis over the results of that. And precisely these let me say this in a different way, I guess. Ultimately, what we end up framing this problem as is some kind of high-dimensional integral over these degrees of freedom. And so maybe to give a bit more of a concrete handle on what that might look like, the simplest possible such theory that one can put on the lattice involves putting a real number on, let's say, every site of the lattice, and encoding somehow the interactions between the values of this field, which takes real values on all the points of the lattice, via some kind of Boltzmann weight or some kind of energy weighting function. So this now starts to look very similar to a statistical lattice problem. Although keep in mind that usually when we're thinking on the statistical physics side, we think of some physical object as maybe the lattice that one is trying to look at thermal fluctuations of. And here there's actually an extra time coordinate. So it's somehow kind of looking at the evolution over time of a field in space, and looking at now not the thermal fluctuations, but the quantum fluctuations. But those words aside, the actual framing of the problem is more or less identical. So really the semantics are encoded in how one defines this weight function. But once you've defined such a weight function, your task is simply to sample over the values of these fields associated with sites and maybe sometimes the edges of the lattice in order to compute particular quantities. And so maybe the primary quantity that you can compute is some kind of normalizing constant, the partition function, as we saw in Michael's talk, which is just the integral of this weight function over all configuration space. And that somehow encodes some physical properties as well about your theory. This relates, for example, to the free energy in some sense, in the statistical sense. But it can also be related to macroscopic properties of the quantum model. However, maybe more interestingly, you often want to take, now I'm using these cheeky bracket notations, you want to take the expectation value of certain observables or certain functions that you can measure of the field with respect to this weight function. And those expectation values ultimately have something to do with the dynamics of your quantum fields. And if you choose the right quantities to look at the expectation values of, then you can extract things like the predicted, say, the mass of the proton, or the predicted interaction strengths of various composite particles that you might form out of these fundamental degrees of freedom.
Yeah, let's go this one.
Yeah.
Just related to the way Michael was presenting things. In there was sort of an interesting what we in statistics would call sort of outfill asymptotics, where you sort of build the model, you have a bigger and bigger lattice, but it's somehow the same Hamiltonian. Whereas here it's almost like infill, where you fix the trick you're looking at, and then you refine that more carefully. Is that correct?
Yeah, I would say absolutely. So the usual picture is that the limit that you're taking is you're fixing some kind of physical volume, and then you're infilling, as you said. So you're just refining the resolution of the lattice. So there is still more degrees of freedom as you go in that direction, but the kind of physical scale associated with that might be fixed to one or a few values. Yeah.
And this lattice isn't a lattice different from the lattice of a material. It's the lattice representation of the space through which particles can move and collide with each other.
Yeah. So I should maybe clarify a little bit. So while we're talking about particles, ultimately, once you phrase this in the mathematical language of the standard model, this is a quantum field theory. And so there's no specific particles on specific space-time points. Rather, it's just the values of these quantum fields throughout all of space-time. But you are seeing their trajectory through some kind of time dimension as well.
That governs how the particles interact with each other as they pass through that step.
Yeah, so if you want to ask how particles interact, you need to now excite some fluctuations of these fields, which are the particles, and then look at essentially the properties of these fluctuations as they talk to one another. Yeah.
Basically, a field is like the superposition of the wave function.
Yeah, it certainly can be related in that sense to the particles, assuming they exist associated with the field. Okay, so this was a bit of a touchy-feely overview, but maybe now we can jump to the blackboard and talk in a little bit more detail about specifically how this lattice sampling problem is formulated, and especially and in particular in the context of QCD, how this is formulated and ultimately how this turns into a sampling problem. Okay, so I guess I don't need to do anything, right? Maybe I should stop screen sharing.
No, you can, yeah. You can
Okay.
discuss.
Okay, great. So then I will just move over to the blackboard and we can continue that way. Okay, so let's be a little bit more precise now. So what are the ingredients in such a calculation? All right, so I mentioned this idea that we have some kind of lattice geometry. So this is a space-time lattice, meaning it's four-dimensional. And I should maybe mention as a caveat that for similar reasons to in the Ising model, we'll often use kind of toroidal boundary conditions, so periodic in all directions. And I'll come back in a moment to how this has to do with time, but in the spatial dimensions, I hope you follow that this essentially reduces the boundary physics, as Michael was also mentioning, and it means that, for example, we can do Fourier analysis now in the spatial directions because everything's translationally invariant. Okay, so we have this kind of a lattice. And so here is maybe a 3D slice of a 4D lattice. And then upon this lattice, we have some kind of fields that we define. And so to be a bit more precise, what I mean is that these are some kind of functions of the space and time coordinates, which, of course, this being a lattice, I can only plug in specific values of space and time. But nevertheless, this is some sort of function that maps from this to, maybe I should say in the following way, this maps from 4 coordinates to, for example, a real value. So each site maybe has 1 real value associated with it. This is the simplest example that maybe you can come up with. More generally, maybe you have some kind of map from these space-time coordinates to some complex vectors, maybe an n-dimensional vector associated with each site. And there might be then some sort of distribution over how these vectors at neighboring sites or nearby sites like to align with one another or anti-align. And perhaps in the most complicated case, we might end up with things, just to note this already, that map from the lattice to a matrix, a space of matrices. But of particular interest will be the space SUN. So just to get a sense, is this familiar to people, or should I go over SUN? Sorry? Omega is some name of an arbitrary field, say, just for example. So I should say these are all examples of fields that we might write down.
So a field is just a function from space-time, lattice space-time to...
Exactly. And so this is sort of the mathematical sense of a field. The practical sense is that a field is something where I associate values to points or edges of my lattice. So you can imagine just a big array in memory of either vectors or real numbers or matrices associated with this geometry.
What is SUN?
Okay, yeah, let me explain. Apologies. Thank you. So okay, SUN is the group of n by n matrices, complex value, complex entry matrices, subject to, oh wait, this is subject to two constraints. So one is that the determinant of whatever this omega is, or the output rather, is 1. And the other is that this is a unitary matrix, meaning that the dagger, which means conjugate and transpose, is its own inverse. So the reasons for why this happens to be a group of interest are a bit obscure, but the relevant note here is that these sorts of matrices for n equals 3 appear in QCD, in the quantum chromodynamics sector of the standard model. So in fact, when we're talking about these 3 colors that I mentioned at some point, those 3 degrees of freedom, the gluons, which interact with those 3 colors of any particle, will ultimately be represented with these kind of SUN matrices and act by multiplication on essentially 3 component vectors. So I'll get to that momentarily, but this is precisely at least the mathematical definition. And so what you can imagine is that in practical language, what this amounts to is just storing n by n matrices associated with sites or, let's say, edges of the lattice. Yeah.
Please stop me if I'm talking nonsense, but in this space, in this discretized lattice, say I wanted to put a single electron in this space, that electron will have a corresponding field that is distributed throughout the entire space, and that field is determined by the standard model, and that's it. So is there something uniquely defined by that single electron sat inside that space?
Yeah. So let me clarify. I guess the electron doesn't generate an electron field, but rather the configurations of the electron field and its fluctuations encode either the interactions of real electrons, or there are these quantum fluctuations.
The electron is the field, not the.
Yeah.
Not the electron
Yes.
isn't creating the field.
Yes.
There is a field, and you can say that's the field of an electron, and that's
Sure.
what's creating an electron.
Yeah, I think that's the right way to think about it. Exactly.
It's not like a topological defect.
It's not a topological defect. Yeah. Yeah, and maybe helpful to keep in mind is, so in this kind of simplest example of just a real valued field, you could concoct a particle associated with that. It doesn't really exist in our standard model, but you could define such a theory. And what you would look at is positive or negative kind of collective fluctuations of this field that has something to do with the particle excitations of that field. So in particular, at the end of the day, what you would actually want to look at is simply something very similar to what you might look at in the Ising model. You want to just look at, for example, okay, maybe my field in some slice fluctuates up and down. You'd want to look at the correlation function between, at some site x and some site y, the values phi and x and phi and y. So this correlation function, which I can, for example, write as the expectation value of the product of these two fields, would, for example, be one of those observables, O, that I might choose to plug in. And that really corresponds to this concept of a particle being created at one site and propagating to a different site. So there's a fairly fuzzy and fairly loose connection to particles. unfortunately, I can't really point you to a particle on the lattice. That's the upshot of this. But these fields are encoding in some sense the fluctuations and propagation of these particles. Okay. Any other questions while we're on the subject?
Why R4 and not Z4? Is it just so that you can change the lattice?
Yeah, I mean, I really should have written something like Z4 here. But of course, any map from R4 to R can be restricted in such a way. So yeah, in general, when we start before the lattice, it's something from R4 to R. And now that we're on the lattice, it's whatever the lattice geometry is, which is maybe something like Z4 in all of these cases. Yeah, good point. Okay, so these are the sort of field degrees of freedom. In practice, they're just some arrays of values that we want to sample over the configurations of, much like, if you like, in the Ising model where we had arrays of up or downs that we wanted to somehow sample according to an energy function. But speaking of energy functions, this weight I haven't really defined. So if you glance back over to this side, the relevant piece of this puzzle, which encodes the actual physics, is this so-called Boltzmann weight, which is just generically, we can write this as e to the minus some real valued function of the field. And in the QFT, quantum field theory parlance, this is usually called an action. So this is something that takes in the entire configuration of degrees of freedom on the lattice. So if you like, in the real scalar field case, this takes in our whole array of real numbers. So generically, I'll just denote by phi whatever fields are being taken as input. And it gives you a real number out, just a single real number out. And this is some kind of measure of how probable this configuration of the field values is. So if you note how this appears inside the weights, a larger value of the action, you can think of in analog to the statistical picture as a larger value of the energy, meaning this should be penalized or should be less likely. And lower values of the action should, maybe in the statistical language, you can think of as lower values of energy that should be more likely to appear in our sampling. Okay, so what precisely this action looks like depends on the theory, and I will define it for QCD maybe in a little bit. But just keep in mind that the usual structure of this is something that prefers that fields somehow have some kind of local alignment to them. So again, going back to our simple example of just one real number per site, you might write down an action that has an energy cost associated with the fields being anti-aligned, or one positive and one negative for neighbors, and instead a lower energy when these fields are both positive or both negative. So the upshot of this is that you have some kind of weight that prefers local coherence, but maybe on the longer ranges, you have some kind of fluctuations as a result of just the large space of degrees of freedom that you have. Yeah?
So now this one we go to action, this phi, it no longer is like a function from Z or R4, but now you have the lattice, which is, let's say, N, or you have A, right? Like A, but you have, let's say, A1 times A2 points, right? That lead in R4. So now you need the function of all of them. You're find all of the A1 times A2 four-dimensional.
Yeah, so just to clarify the notation, the A I would use to represent the distance between neighboring sites, but let's call the number of sites on one side L, something like this. So exactly, you have a function in this case maybe from L to the fourth values to a single number. And those are the values of whatever the field values are on all of the sites of your lattice. So maybe you have like minus 0.5 here, 0.3, etc. This vector of all these numbers is the argument of that function. And the answer, or what the function reports, is what is the action associated with this. So in other words, how penalized or how favorable is this configuration of the field? Yeah, no problem.
S represents the field theory.
Yes. Yes.
So it's a pure bijection. So to a field, to a quantum field theory corresponds like unique S and inversely S determined quantum field theory on the lattice.
Yeah, on the lattice. That's the caveat. So
I guess when the number of points exceeds, then you have sort of an infinite number of products of these integrals in them, which I imagine cause troubles to people.
yes, and in fact, this is the reason that one goes to a lattice in the first place, because it would be essentially impossible to represent an integral over some kind of over the space of continuous fields that would be ill-defined. So this is some kind of regulator for that space, if you like. After doing that regularization, you can say there's a pretty constrained map between the action S and the theory. So the action S is really encoding the physics of the theory on such a lattice discretization. And now you try to simulate or sample at a variety of different lattice spacings and then extrapolate towards the real theory, which is when this lattice regulator or the lattice spacing is taken to 0.
In principle, if I have a S of 5, which we can just think of a maybe linear or non-linear map from specific functions to R, just an operator. I can have like integral of 5 or whatever. Do people usually think in continuous terms and then look at how to discretize them in a lattice model, or do they? Well, I don't know. Do they don't?
Often, yes. You'll start from some continuous representation of the action, which you can maybe write as some like integral over 4D spacetime, this coordinate, and then there's some, you would call this the Lagrangian density in terms of the value of the field at x, as well as various, let's say, derivatives of the field at x. So this would be maybe what you start from, some kind of completely local density that you integrate over a continuous space. So this is something that would be well defined even in the continuous theory. The problem arises when you try to do this high dimensional or then infinite dimensional integral over the fields, which is now an ill-defined concept. And so one should discretize this somehow to arrive at, to arrive at some kind of action that one can evaluate on these discrete fields, which have only a finite number of degrees of freedom.
And is there a way, at least for natural Lagrangian functions, to make sense of these models in continuous limits?
So are you asking whether this Lagrangian can be defined in the continuum?
Natural choices of L meaningful limits when the number of lattice points goes to infinity.
Yeah.
Continuous limits.
Yeah, I would say so. So one can really define a very meaningful function here, even in the continuous limit. And so if you like, the process could be phrased as you start from that continuous Lagrangian, which is really what you think defines your quantum field theory. And then you somehow discretize it by, for example, discretizing these derivatives onto the lattice, and then taking all the functions of phi and leaving them probably untouched because they still work as they're local. And so then you turn this into some sort of sum over some discretized version of this for your given lattice geometry that you're looking at. Yeah, precisely.
Can I check I'm getting this right? You've got your phi that maps to space-time as latent space. And then you have your S that gives a weighting pointing to latent space, and then you have a distribution that's defined in terms of that S specifying the potential.
Precisely, yeah. Yeah, so this is very similar to the statistical models approach. Once everything's cast in this language, I mean, really, the translation factor happens before this step, where you go from this quantum theory that somehow has to do with particles in this fuzzy way. But once you've changed this into some kind of degrees of freedom on the lattice and some energy function over those degrees of freedom, you have just an ordinary looking, let's say an integral over these degrees of freedom weighted by some positive weight. Which, as you might imagine, naturally maps then onto a sampling problem with respect to those positive weights. Okay.
A second, but I thought that S was already the potential. I thought you need a distribution to tell you how likely.
Yeah, S is the potential, yeah. Maybe did I mishear what you said about the potential? Yeah, yeah. Yeah, if you like, S is like beta U from Michael's talk. It plays exactly the same role. Yeah.
I'm not sorry if you already said it, but why do you have to discretize?
Yeah, no, this I didn't go into detail on this because it's somewhat of a technical reason, but essentially it amounts to what you'd like to do is integrate over all configurations of a field with respect to this weight. And that's an ill-defined space in some sense, because that in principle also includes fields that are extremely pathological, that discontinuously jump at some point, or that have very arbitrarily rapid oscillations included in them. So you can regulate that space in a number of ways and make it well-defined, and this is one such option, which essentially reduces then your infinite, ill-defined initial integral into an integral over a finite number of degrees of freedom, so that ultimately you have something that looks really, as I've written there, it expands out maybe into an integral over, a product of a finite number of phi x degrees of freedom over some well-defined space. Yeah, so it's really just it's a regulator to make that integral over field configurations well-defined.
Is it then well known that once you compute your expectation value, you then take the limit in which the lattice spacing out goes to 0? Is that then well defined? Is that an unknown? Depends on the quantum field theory.
It depends on the quantum field theory. That's correct. What appears to be the case. Okay, so there's a few different things. One, you can make numerical observations that indeed this works by just taking the limit numerically. One can also make some kind of perturbative arguments of the style of these, Feynman diagram expansions that one does for other sectors of the standard model, just to try and constrain this part of the limit, because somehow one can make comments about perhaps not exactly what the results are, but that this is the type of terms that I expect in my extrapolation and things like that. So there are slightly more rigorous things that one can do, but ultimately I would say this boils down to you run the simulations and you look for a well-defined limit of your observables. More or less. Yeah. Okay. So maybe this is a good point to take a quick break, since we are close or just over the hour, and then we can continue on. Quarter past, yeah? Does that sound good? Okay.
I think better if you stop sharing, if you don't use the slides anymore. Because
yeah, I can stop sharing here?
I'm gonna stop recording and see what I record.